Optimization tools and the Ляпунову stability problem. Of course, everybody learned the Ляпунову stability problem in university, so this is usually the second year of education, very basic differential equations. What is the, why is it necessary? So what needs to use modern convex optimization there? It seems that everything is clear, so everything can be determined by just by computing the leading eigenvalue. But there are several problems in Ляпунову stability which are quite challenging for numerical analysts and for people working in optimization. We will talk about two of them. First of all, how to make a system stable by changing some of its parameters. Such a problem naturally appears in applications, for example, in sociology, in population dynamics, and in mathematical economics. In mathematical economics and in population dynamics and mathematical ecology, they use upside-down terminology. So the system is stable when it grows, when the spectral radius is bigger than 1. And this makes sense because, for example, in mathematical ecology, if the if the solution tends to 0, this means that everything will die. So there will be a desert. And so very desirable for both economists and ecologists to have the stability in their sense, so that the whole trajectory will grow. And how to make, for example, if we have the linear system, the usual linear system, how to make it stable if it's unstable, and how to make it possibly with a small perturbation of the system, because in those applications, every perturbation costs a lot. So it really costs money. In mathematical ecology, it's called calibration of matrices. So how to calibrate some parameters. For example, if we study populations of some, I don't know, insects in a forest, then if we see that some population goes down, then we should do something with this ecological system. It might be very expensive. And the same, of course, in mathematical economics. So this is the first problem. The second one, studying the stability of more complicated systems, of linear control systems, and how to design the stability in this case. And in this case, this definition of invariant Ляпунову function and John spectral radius worked and matter a lot. Some definitions have been given by Tatiana already. We start with the first problem. So this is a usual dynamical system where A is a constant matrix. Of course, the system is stable if all trajectories tend to 0, and this is so-called Hurwitz stability. And the Hurwitz stability is equivalent to the condition that all eigenvalues are on the left-hand side of the complex plane. So all eigenvalues have a real part strictly negative. And the linear dynamical system with discrete time. So there's a discrete time counterpart of it. So we discretize the system. This will be the system of difference equations. These are not just discretization of linear systems. So this system has its own wealth. Because, for instance, if we have some periodicity of the system, depending for example, in population dynamics, they count time by years, so that time is discrete because of periodicity of weather, of the climate every year. And the stability of such systems are called sure stability. And of course, it's dictated by the modulus of the all eigenvalues. So all moduli of eigenvalues must be smaller than 1. So the spectral radius of the matrix A smaller than 1. For the sake of simplicity, we concentrate on a positive linear system. A system is called positive if every trajectory which starts is in the positive orthant will stay in this positive orthant forever. For a discrete time system, this means that the matrix A is non-negative. For the continuous time system, this means that the matrix is so-called Metzler matrix, which means that all off-diagonal elements are non-negative. The diagonal can be arbitrary. Of course, the non-negativity of the system simplifies the problem a lot, because all matrices, all, let's say, non-negative matrices, they work in the same direction, so there is no cancellation rule at all, and etc. And of course, we have in our hands the Perron-Frabenius theorem, saying that the leading eigenvalue, the biggest bimodulus eigenvalue, is always realized in some positive eigenvalue and the corresponding positive eigenvector. So instead of working with all eigenvalues, we can just take the leading eigenvalue, which is the positive, the biggest bimodulus. And so we consider a positive linear system, and there are two problems. So if we have a linear system, let's say matrix, one matrix, how to make it stable? In other words, how to find the closest stable matrix to this matrix in some norm. So the closeness is measured by some norm. And the second problem is how to make it unstable. We already mentioned that many people from applications called stability instability and vice versa. So we study simultaneously both problems. The second one is simpler. So actually for the second problem, it is almost always possible to find global minimum, and even sometimes it's possible to find a solution in an explicit form, in a closed formula, in contrast to the first one, which is hard. Of course, the set of stable and the set of unstable matrices are both open. Yes, the spectral radius is strictly less than 1 or strictly bigger than 1. And that's why the problem doesn't have a correct solution. There is no closest. And therefore, we have to take a closure. So we can consider the following problem. A is a given matrix. We need to minimize the distance to the closest possible matrix A, whose spectral radius is equal than 1. It might be less than or equal than 1 in the first problem, or bigger than or equal to 1. The set of stable matrices have pretty complicated structure. It's not convex. And actually, if we measure the closest distance to this set, a lot of local minima or local stationary points appear. And of course, the distance should be measured in this most popular matrix norm. There's a Frabenius norm. Roughly speaking, the Frabenius norm of a matrix is a Euclidean norm of a vector, if you consider this matrix as a vector in square dimensional space. You see the list of people who studied this problem. List is far from being complete. One of the most prominent work was done by Yuri with his co-authors, Orban Dexivry, he's a PhD student in Leuven-Lenov, and Paul van Doren. They propose absolutely new idea how to at least write some lower and upper bounds for the answer, because they inscribe Deacon ellipsoids in the set of stable matrices. This is very delicate technique, and it really gives some approximate solution with some rate of approximation, because the first co-author, he programmed it, and the program is available in internet. My co-author Nicola Guglielmi and myself, we in 2018 proposed another approach of solution of this problem. But before talking about this idea, let me only mention that we constructed some examples when the number of local minima can be exponential in the dimension. This probably means that the problem doesn't have polynomial solutions, but we don't have any theoretical results on the complexity of the problem. So our two problems, minimizing and maximizing the spectral radius. And the general problem, of course, is to maximize or minimize the spectral radius of some matrix set. In our case, in the case of the searching for the closest stable matrix, this set is just a unit ball in the set of matrices. But it can be arbitrary. And even for convex matrices, the problem is hard. And there are two explanations for that. Two very, let's say, regretful properties of the spectral radius as a function of matrix. First of all, the spectral radius is neither convex nor concave. The second, the spectral radius may lose Lipschitz continuity. It happens when we have multiple eigenvalues. Of course, we can object that, well, multiple eigenvalues, it's very rare. So actually, the random matrix don't have multiple eigenvalues. But this is only the part of the truth. Because if we introduce, because the point of local minima usually does have multiple eigenvalues, which is very natural. If we find a local minimum to this problem, then the point of local minimum possesses some singularity, and this singularity is crucial. So it makes all known algorithms to suffer around the point of local minimum. Well, this is elementary numerical example. We consider two matrices, 4 by 4. Both of them are non-negative. And we just change the position of two elements. So one element is 1, the second element is on diagonal 1/2. And we put this one a bit, we shift it to the left down, and we shift to the right down the diagonal element. Nothing changes more. Just we change the location of two elements, and we consider the matrix segment. We consider the convex hull of these two matrices. And now let's see the behavior of the spectral radius as a function of matrix. This is the graph. So we see that already in this example there are 3 stationary points, and some of them are non-differentiable at all. In this example there are no multiple eigenvalues, but very often it, as I mentioned, loses the Lipschitz continuity. Well, how is it possible to attack this problem? For non-negative matrices, we can fix the position of the eigenvector and try to optimize to find the closest matrix with this fixed position. So assume that our matrix is non-stable, so assume that the spectral radius is bigger than 1. We need to find the closest matrix whose spectral radius is equal to 1. Instead of minimizing the spectral radius, instead of considering the set of matrices with the spectral radius less than or equal to 1, we just fix the Perron eigenvector and make the optimization among the set of matrices with this Perron eigenvector with the leading eigenvalue 1. Of course, the problem becomes simple. This is a quadratic problem with linear constraints, and moreover, this quadratic problem is not over the dimension d square, that on dimension d, because this minimality, the minimality of the Frabenius norm, can be done row-wise, in each row separately. So the problem is simple. Well, we fix the Perron eigenvalue and make this minimization. What next? Well, so we took this Perron eigenvector, we squashed everything we could do from this equation. So among all matrices with this eigenvector, we found optimal. But nobody guarantees, of course, that this eigenvector is optimal. So we should somehow vary this eigenvector. But after that, the problem immediately becomes very hard. What can be done next? Well, but this matrix actually has two eigenvectors, one on the left and one on the right. And this was the right eigenvector. And let's try to now to fix the left eigenvector and multiply by the left eigenvector. So this matrix has an non-negative eigenvector, and it has the invariant hyperplane. And we optimize over all matrices that have the same invariant hyperplane, which means the same, the fixed left eigenvector. And then we alternate left and right, until, who knows, if we have some convergence. It's a bit surprising that these left and right eigenvectors really leads to a solution. And this theorem claims that if the limit matrix, the limit always exists, if the limit matrix is totally positive, so if there are no zeros, then it converges to the global minimum, to the global solution. In spite of non-convexity, in spite of everything, so we get a global minimum. Unfortunately, this situation is not, of course, it's not standard. So it's very, very desirable and quite exceptional that the resulting matrix doesn't have zeros. And now we need to turn to sparse matrices. Sparse matrices, sometimes they are very convenient. For example, if we numerically solve linear equations, sometimes sparsity spoils a lot the problem, makes it much harder. For instance, if we compute the eigenvalues by simple iteration method in the page ranking problem. And this problem also very sensible with the sparsity, because what happens? If our limit matrix is irreducible, which means there is no subspace, no negative invariant subspace, then the process converges to a local minimum, but it's possible to find an absolute minimum after that. So it's possible to pass from the local minimum to the global minimum. But the most complicated case if the limit matrix is reducible. In this case, of course, the matrix has the factorization, upper triangle block factorization. And after that, this block factorization will be local minimum. And after that, the problem becomes, the problem is decomposed in two problems of smaller dimension. But after this, it is impossible to come back to the original problem. So this decomposition will stay forever, even if the absolute minimum doesn't have this decomposition. And after that, we go further by the same algorithm and so on. And the decomposition may take several iterations. It's possible to, this is an example borrowed from the paper of Anderson. We just compared our algorithm, the efficiency of our algorithm with his algorithm. But you see that the matrix is totally positive, and the spectral radius is bigger than 2 and 4, so this is unstable. And the closest stable matrix looks as follows. And unfortunately, we see that the matrix is factorizable, yes, because of this last row. So it has factorization. And that's why, to solve this problem completely, we should make some exhaustive search along the factorizations. But of course, in the dimension 5, this is possible, but in the dimension D, the problem becomes enormous. But at least it converges to a local minimum. What can become out of this situation? We can try another norm. Of course, another norm would be not that important for applications. Of course, everything should be done in Frabenius norm. But if we see that in the Frabenius norm the problem is hard, Let's try another norm, and this is our joint work with Yuri. When we try to attack this problem using L infinity L1 norm, well, there's no, of course, dual to each other, and the problem look more or less the same. Instead of rows, we can take columns, and that's why let me just explain this problem for the L1 norm. So L1 norm is the maximal sum of elements in the row, in each row, computed over all rows. And we need to find the minimal tau such that the matrix can be made stable or unstable by changing elements in each row by at most tau in the L1 norm. So the problem can be solved row by row. The set for each row has its own unit ball in the d-dimensional space. This is L1 unit ball. So this is actually cross polytope, octahedron, multivariate octahedron, and it can be given by as convex hull of 2D points. And we come to the concept of so-called the family of matrices of row uncertainty sets. It was introduced in the joint work of Yuri and Vincent Blondel. Such a family consists of matrices in which all rows are taken independently of each other from special sets. So the sets are fixed. And they're called uncertainty sets. If the uncertainty sets are finite, then we can imagine the following situation. We have a choice among 4 rows, 4 elements in the first row, so we can put every row separately. We don't have choice for the second row. And we have choice between 2 rows for the last row. So in total, we have 8 matrices. And of course, we can solve it just by exhaustion of 8 matrices. So it will be immediate. The same is true when our uncertainty sets are not finite but polytopes. This is the same because taking the convex hull, nothing changing nothing. But unfortunately, in general, the exhaustive search is hard because already a Boolean cube, when we have just 2 elements for each row, contains 2 to the power of 50 elements. And it's possible to consider them all. The product families with row uncertainties, they have been considered in different contexts. For example, Viktor Kazyakin applied these problems for so-called asynchronous systems. And one of the most natural applications is Leontief input-output model in mathematical economics and so on. About the spectral graph theory, I will mention it shortly. How to optimize the spectral radius over a product family. It appears that the product family is quite convenient object for optimization of the spectral radius, for optimization of the Perron eigenvalue. And so this is some papers when this problem has been started. This first idea introduced by Nesterov and myself, this is so-called spectral simplex method. It looks very similar to the policy iteration method in Markov decision process. And some people even claim that this is the same. For example, when we sent our paper to John Tsitsiklis, he said, well, guys, relax, this is known for decades, because this is a policy iteration method for MDP problem. But then we didn't know much about Markov decision processes. I studied literature about that, and I found, to our to our happiness that this is not the same. So actually, the algorithm indeed looks similar, but it has actually nothing in common with the algorithms of Markov decision processes, and moreover, they are in some sense incomparable. We will see what happens. The spectral simplex method consists of recursions. This is a relaxation algorithm, and each iteration is a one-line correction of a matrix. So we have an initial matrix, we compute its Perron eigenvector, and we replace the first matrix to the first line to the line optimal in some sense with respect to this Perron eigenvector. So actually it can be shown very simply. So assume that V is a leading eigenvector, and this is the set Fi. So this is the set of points for ith row of our matrix. So we can choose every row we want. And the optimal strategy is to choose the one with the maximal projection. So we choose this row, and we put this row into the ith position. So we make one rank correction of a matrix. And this is the theoretical base of it. So if it appears that the previous row is worse than the optimal row, so this is the optimal row and this is the row, the current row in our matrix, then if the matrix is strictly positive, then the spectral radius strictly increases. And vice versa. So it strictly decreases if we take this. If we minimize the spectral radius. What happens if we check all the rows and we found that it's optimal in all rows separately? This means that we found a global minimum. This makes it really, let's say by spirit, really similar to the spectral simplex method. And this notion was suggested by Yuri. This is just the algorithm. This is a program. It's very simple. And for strictly positive matrices, the spectral simplex method is well defined, the relaxation, and it always converges within finite time, provided every uncertainty set is a polyhedron. However, here I should stress it is strictly positive. What happens if the matrix has zeros? It appears that for sparse matrices, the algorithm cycles. And moreover, for the minimization problem, it cycles very often. Again, the reason is that when we're looking for the minimization, then around the local minimum, we have the singularity. We have many eigenvalues almost equal to each other. And if all those eigenvalues equal, then the algorithm cycles. It seems that it's not a problem because we can, for example, we can perturb all the coefficients, but after the small perturbation, we can go a wrong direction of the algorithm and eventually come to the point which doesn't have anything in common with the absolute minimum. So the positive perturbation of a matrix does not do the job. And what to do in this situation? So we left it as it is. So we left it with this trouble. We invented another algorithm based on convex programming, which also can be applied to minimization of the spectral radius within the product family. But this problem, of course, stays as a source of worry. And in several years, I published the second paper when I managed to resolve this trouble with the cycling. And the solution appeared to be, at least theoretically, very simple. The proof is quite hard. And the fact is the following. Assume that our matrix has a unique leading eigenvector. So this means, in other terminology, the geometrical multiplicity of the Perron eigenvector is equal to 1. Geometrical. So there might be, they may have multiple leading eigenvalue, but the geometrical multiplicity, the leading eigenvector is unique. Then, after every one-line correction, this property remains true. This means if we take some good initial matrix, then this good property will go through all the iterations, and in this case there is no cycling. It's possible to show. So that's how the cycling phenomena can be resolved. We just take a good first matrix, and after that the matrix can become sparse. Yeah, lots of zeros can appear. It may be reducible and so on. But the geometrical multiplicity of the leading eigenvector will stay the same and will stay 1. Well, these are numerical results. We see that it really works efficiently. For example, in the row, we indicate the number of elements in each uncertainty set. We assume it's finite. And in the column, we indicated the dimension. For example, in the dimension 100, in the Boolean cube, when we have just 2 rows, of course, the Boolean cube has to the power 100 vertices, but the spectral simplex method does just 56 iterations. And within 12 seconds, it finds the absolute minimum. If we consider less dimension, for example, the dimension 10, but all our uncertainty sets become more complicated, consisting of 100 points, it still works fast, just 0.3 seconds. Even in very high dimensions, so it works in up to dimension 500, but actually then we made a modification of this algorithm working in much higher dimensions. Theoretically, the convergence is linear, where Q is something which less than 1. Unfortunately, all attempts to somehow to separate this Q from 1, they all fail, so this is more or less a purely theoretical result. But anyway, we will remember it because to compare with the so-called greedy strategy for the same problem. Well, let me mention again that solving this problem of optimizing the spectral radius actually solves the problem of the closest stable matrix in the L1 norm or in L infinity norm. We should only take all these uncertainty sets to be L1 balls in d-dimensional space. What happens if we try to optimize all rows simultaneously, not just one by one? Because in this spectral simplex method, we make one line correction, after which we recompute the spectral radius. We recompute the new leading eigenvector. And then we start with the first row again. If it's optimal for the new eigenvector, only after that we go to the next line and so on. What happens if we try to make the optimization in all lines simultaneously? And here some unusual phenomenon came because trying for the small dimensions, this algorithm suffers. So it works much worse than the spectral simplex method. And the reason is that, well, okay, assume that we optimize on the first row. But the leading eigenvalue changes. And therefore, if you try to optimize in the second row using the former eigenvector, then we already spoil the whole matrix. We come further from the optimal answer. And so the next lines can spoil the previous iteration. But this idea was suggested by Akian Gaubert, Grand Clement, and Julia in 2017. But then a student of mine, Alexander Tsvetkovich, he tried it for high dimensions. And for high dimensions, the result was quite unexpected, because in high dimensions, it works much better than in low dimensions. So you see that in dimension 2000, this greedy strategy, when we once compute the eigenvector and then optimizing all rows, it in average, after several, after I don't know, 30 or 40 experiments that he made, it takes 4 times 1 iterations. Between 4 and 5 iterations, and the optimal solution is found, the global minimum is found. And you see that with growth of the dimension, the number of iterations reduces. So it's a kind of bliss of dimensionality. This phenomenon is not fully explained. So we have some arguments why it happens. And the algorithm, as a base of this algorithm, the following result, because the greedy strategy is the greedy strategy has a quadratic rate of convergence, but of course under some conditions. First of all, the quadratic rate appears only for totally positive matrices, so no sparsity is possible for this result. And second, all the uncertainty sets must be smooth. So there may not be, for example, finite sets. But at least this is a kind of argument about this fast convergence. Well, unfortunately, very small formula here. I will explain. The constant b in this parameter of quadratic convergence is proportional to the maximal Gauss curvature over the minimal Gauss curvature. So we consider C2 surfaces which are strictly convex. And this is a constant b, the constant of the quadratic convergence. So we see that if the set is not smooth, it doesn't work. But at least this is some argument for the efficiency. Well, unfortunately, what happens if this is not totally positive? It may cycle again. And it happens not so often than in the spectral simplex method, but sometimes it happens. This is the simplest example of the cycling. And the most dangerous phenomenon here, then after the cycling, we choose among several matrices of the cycle, and all of them are worse than the absolute minimum. So, okay, assume that we have some cycling. Well, like in linear programming, let's take one of them, and it should be optimal. No, here it's impossible. It will not be optimal. The optimal element will be very far from it. What to do with the cycling? Well, to do this, cycling happens because of the non-uniqueness of the leading eigenvector. So the leading eigenvalue 1 can be multiple. Therefore, let us, in some sense, generalize the notion of the leading eigenvalue. We add the identity matrix to the matrix I. We add the matrix of ones. This can be every rank 1 matrix. Not necessarily the matrix of ones, but for the sake of simplicity, let's take the matrix E and multiply it by a small number epsilon. Of course, after that, the matrix will be totally positive, and it will have a unique leading eigenvector up to normalization. Very good. And then we take epsilon tends to 0. And the question arises, what can be said about the limit of this unique eigenvector? And if we take this generalized leading eigenvector, which is always unique, then the greedy method doesn't cycle. We can take this eigenvector, but of course the question arises how to find this limit. Of course it can be found easily if we take the Jordan form, canonical Jordan form, but for high dimensions this is, of course this is impossible. And this generalized eigenvector can be computed as follows. This so-called selecting leading eigenvector. We find the leading eigenvector by the simple iteration method, starting with the vector of ones. And the process will converge to the selected leading eigenvector. And that's for if we compute the eigenvectors by the simple iteration method, the process will never cycle. Of course, we do not apply it for all iterations. Only if it cycles, we can apply it. And this is how to find the closest stable matrix in L infinity norm. We just fix some tau. We solve this problem of optimizing the spectral radius over the matrix ball, and then by the double division, we find very quickly the optimal solution. About the complexity of this method, we know nothing. Probably this is the same situation as for linear programming for the usual simplex method, because numerically it's excellent, but maybe someone could come up with an example, something like Clementi example, when showing that this method is actually theoretically bad, is exponential. We don't know the answer about the complexity neither for the for the simplex method and for the greedy method. For us, this is still unknown. One application about the maximal, about the closest stable system, the maximal acyclic subgraph problem, MAC. And the problem consists in finding the smallest number of edges, then can be cut off to make the graph acycling. So we need to destroy all cycles. So here we have 3 cycles. And to destroy them all, it suffices to eliminate, to remove 2 edges. The graph is directed, of course, this is the graph. So the number of the remaining edges is 5, and 5 in this case is the best number. Well, with respect to complexity, this problem is very well known. This is NP-complete, and this is one of the first examples of NP-complete problems. It was on the list of 21 NP-complete problems of Karp in 1972. Of course, one algorithm can be immediately suggested. We can enumerate all vertices. We can assign a number to each vertex, and we can leave only vertices which increase the number from 1 to 2, from 2 to 3, and so on. Of course, no cycling is possible here, and we can leave only those vertices. For example, only red ones. Or we can leave only remaining vertices, because among the remaining vertices, the cycling is also impossible. And of course, the approximation factor here is 1/2. So we make some enumeration, and we take one of the 2 sets of edges. And one of them, of course, will contain at least half of the edges. And surprisingly enough, this simple algorithm is still not beaten. So this is the actually best known algorithm, at least theoretically. Nobody comes with the algorithm which has theoretically the approximation factor bigger than 1/2. The NP completeness is not only for the exact solution of this problem, but for the approximate solution with the factor slightly less than 1. So even approximate solution of this problem is an NP-complete problem. And that's why, of course, there is bulk of literature on this subject. There are many algorithms, genetic algorithms, and so on. Some global optimization is applied here. And all of them, if the approximation factor numerically slightly exceeds 1/2, for example, 0.55, this is already an advantage. This is already an achievement. It's interesting that this problem has something in common with the Ляпунов stability problem for the discrete linear system, for the search of the closest stable matrix. The point is, the graph is acyclic if and only if the spectral radius of its adjacency matrix, so as usual we associated adjacency matrix to the directed graph. If this adjacency matrix has a spectral radius 0, then the graph is acyclic and vice versa. For example, in our graph, we eliminate these two vertices, which means that we put zeros in these two places, after which the spectral radius becomes 0. And now we see that we have the following problem. We have to minimize the Frabenius distance. We have to find the closest matrix, closest in the Frabenius distance sense, for which the spectral radius is 0. If we replace here 0 by 1, we get our problem for the closest stable matrix. So you see the problems pretty similar, but instead of 1, we have 0 now. And the idea is to apply the greedy algorithm now to this problem, not to the stability problem. An application to the greedy algorithm so first of all, it's very fast. Yeah, as we mentioned, for the dimension 5,000, it works. And second, the numerical results are not that bad. Of course, we don't have any theoretical result, and most likely it's impossible. But for example, for usual matrices with a sparsity parameter about 1/2, so the last line, the approximation factor much exceeds 1/2, 0.6. For sparse matrices, it's a bit worse, but also almost 1/2. No theoretical result that proving this efficiency is known. This is just numerical results. And now let us turn to the second problem I promised. This is the problem of Ляпунов stability, but not just for the linear system, but the so-called linear switching system. In the linear switching system, we have a difference equation. We consider only discrete now. We consider difference equation, xk plus 1 is equal to a of k xk plus 1, but you see that a of k is now not constant matrix. A of k can be taken from the control set. And this control set, again, this is in general every compact set, but again, for the sake of simplicity, assume it's finite. Actually, if we could do anything with the case 2, A1, A2, then the same trick, the same idea can be applied for every compact set. So the notion mainly starts with 2 now. There is no much difference between 2 and 1,000 or 2 and every compact set. But already with 2 matrices, this problem is non-trivial. And this stability now means that all trajectories converge to 0. So this means that the fastest growing trajectory converges to 0, in spite of, independently of the choice of our matrices. So this is a controlled system, and independently of the control, it must be asymptotically stable. In 1988, Nikita Barabanov proved that criterion for the discrete for the stability, and this criterion is based on the notion of the Jones spectral radius. Well, the story of the invention of this notion is really amazing. So first of all, the Jones spectral radius, Tatiana already defined it. But anyway, let's refresh our memory. We have several matrices. Maybe complex, maybe real, doesn't matter. We will focus on the real case here. For every k, we consider all products of those matrices of length k, repetitions permitted. So all products. And we find one of them with the biggest norm. And we take the power of 1 over the length of the product, and then the lengths tend to infinity. It's possible to show that the limit always exists. Moreover, this limit doesn't depend on the matrix norm. So in the first problem, the closest stable matrix, the choice of the norm was crucial, as we remember. Here, it doesn't play any role, because as we know, all norms in finite dimensional space are equivalent to each other up to multiplication by a constant. Here, this constant will be eventually killed by the power of 1 over k. So every matrix norm gives the same definition. And this notion was invented in 1916 by two very young guys, unknown for the wide mathematical community. And in the future, both of them became outstanding mathematicians. The first one is Giancarlo Rota, a famous specialist in function analysis. The second one is his advisor, Gil Strang. He mostly known by his works on the numerical linear algebra. Giancarlo Rota was 19, he was a student. Gil Strang was 27. They wrote a paper on the note of the Jones spectral radius, where they tried to generalize the Hahn-Banach extension theorem to normed algebra. And they found the answer in terms of the Jones spectral radius. They were absolutely sure that nobody would be interested in it. And that's why they submitted the paper in some low-ranked journal, and it was published. And for 30 years, nobody needed it. But in the late 80s, several groups of mathematicians, independently of each other, came to this notion in their problems. And one of them are linear switching systems. Another one is the subdivision schemes, the numerical method of generating surfaces and curves. In wavelet theory, we will not talk about it. So we are interested only in the first. The Jones spectral radius is responsible for the stability, Ляпунов stability of the switching system. This is a measure of the Ляпунов stability. What can be said about the Jones spectral radius apart from its terrible definition? Geometrically, this notion means that there exists a matrix norm, operator norm, where all our matrices defined contraction operators. There are many statements of problems in function analysis, for example, when let us take several contractions, contraction linear operators. But what does this mean? Contraction in which norm? It may be different. It may be contraction in L infinity, but not contraction in L2. So in this case, this statement is very general. There exists a matrix norm, so in the sense of Minkowski, there exists a convex body, symmetric convex body, in which all our matrices are contractions. So there exists a convex body which is mapped into itself by all matrices of our family. This is equivalent to the inequality that the Jones spectral radius is strictly less than 1, and this is equivalent to the stability of the system. Let's see. This is a list of applications, but let me immediately turn to the computation aspects. How to compute the Jones spectral radius? The usual spectral radius of a matrix, as we know, can be computed just simply by computation of its eigenvalues. Unfortunately, there are no formulas expressing the Jones spectral radius by the eigenvalues, and possibly they cannot exist because of these three negative complexity results of Blondel's cyclics. for non-negative matrices that take 3 rational values, 0, 1, and another rational number, the problem of computation of the Jones spectral radius is already in p-hard. For general matrices with rational coefficients, this is algorithmically undecidable. But of course, if you work with engineers, they would say to you, this is very interesting, but this must be computed. How to compute it? Of course, if we somehow find this norm in which all matrices are contractions, then everything will be done. But what does this mean, find the norm? This means to find a convex body in d-dimensional space. There are too many convex bodies. And that's why the standard optimization approach might be to find this convex body among some class of bodies. And this gave birth to several numerical algorithms. The best ellipsoidal norm this idea originated with Ando and Schick in 1998. Then it was independently invented by Nesterov and Blondel and Theis. And in contrast to Ando and Schick, they applied some SDP for this problem, and they got, of course, it's impossible to compute, to get a good approximation, because there's no guarantee that our convex body will be close to some ellipsoid. But at least some upper and lower bound have been computed. Jungers, Blondel, and myself, we introduced the Conic programming approach to compute not the best ellipsoidal norm, but piecewise ellipsoidal norm, and the situation slightly improved. Another approach was suggested independently by many people, including myself and Blondel, Nesterov, and Zhou from Hong Kong. This is a called tensor product of matrices. In short, we try to find the optimal convex body among a given optimal norm given by homogeneous non-negative polynomials. Unfortunately, this approach is very inefficient. So all estimates are pretty rough. And it works only in small dimensions. So when dimension is higher than, let's say, 7, it already doesn't work. A very interesting approach was suggested by Parillo and Jadbabai, sum of squares. So they find the best norm among the sum of squares polynomials. So you see that there are several numerical methods which try to come from several directions to this problem. This is George Poya. In his book Mathematics and Plausible Reasoning, he said that sometimes easier to prove more, which means that sometimes it's helpful to put some more ambitious goal. More ambitious goal sometimes is easier to solve. This is an explanation of George Poya. When trying to prove something, often a good strategy is to try to prove more. In the case of numerical computation of something, for example, with the Jones spectral radius, when trying to compute something approximately, this is not, of course, George Poya, this is already we reformulated, especially for numerical mathematics. When trying to compute something approximately, often a good strategy to find it precisely. If we cannot find approximately, let's try to find it precisely. How is it possible to find it precisely? Because these negative complexity results just prohibit us to do that. But, well, we can be expired by the same example of Simplex method, linear programming, which is extremely bad theoretically, but it works. This is the invariant polytope algorithm by Nicola Guglielmi and myself from 2013, which find the precise value of the Jones spectral radius. How does it work? We, by branch and bound algorithm, find a long product whose spectral radius much exceeds the other products except for the circle permutations of this one. And then we try to prove that it is realized on some norm, and we construct stepwise this norm as a polytope in d-dimensional space. Well, surprisingly enough, it works. And it works in 100% of matrices randomly generated and matrices from applications. What about the invariant function? Because this polytope is not a norm yet. What about the invariant function? It would be a mistake just to take the Minkowski norm of this polytope. For the invariant function, we need to compute first the polar to this polytope, and then to pass from our original matrices to the transpose family of matrices. And this is one illustration for the dimension 3 by 3. This is an invariant polytope from the invariant polytope algorithm. And this is what we get after the polar transform. And this is an invariant Ляпунов function, which proves the stability of the system. And it finds the precise value of the Jones spectral radius. Of course, sometimes we can have leading eigenvalues which are complex. In this case, the polytope must be not a convex hole of points, but convex hole of several two-dimensional ellipses. Well, this is already some recent technique we introduced with my co-author Thomas Maestrik from University of Vienna, how to construct the elliptic polytope. And the construction of elliptic polytope, surprisingly, is a quite challenging optimization problem. For example, we still don't know if it's NP-hard or not. It can be reduced to several optimization formulations. For example, to maximization of a positive semi-definite quadratic form over a polyhedron. Whether this quadratic form of rank 2, of course, whether this is NP-hard or not. Without rank 2, of course, it's NP-hard. If you want to maximize positive semi-definite form. For the rank 2, nobody knows. But fortunately, the invariant polytope doesn't require the precise solution. The approximate solution would be enough. And approximately, there are several methods which solve this problem of constructing the convex hole of several ellipses. Let me stop on this moment. Thanks very much for the attention. Yes.
Thank you. Thank you. Dear colleagues in Zoom, maybe you have questions. If so, please ask.
I think I have a question. This is Jérôme Bolt.
Yeah, Jérôme, please.
About this joint spectral radius, does it have many critical values? I didn't understand about that. Do you have many local minimizer to the problem? Or
Excuse me, do I have what? Because I didn't hear you well.
can you show the slide with the joint spectral radius? The definition.
Can somebody help me in understanding the question? Because
so so you're looking for a polytope that is stabilizing.
yes.
Yeah.
Yeah.
And is this problem convex or
no, this is not convex. So if we consider the class of all polytopes, for example, with a given set of vertices, this is not a convex problem. But it can be solved, let's say, step by step by relaxation algorithm. We start with the leading eigenvalue of the leading product, of the dominant product, for which we suppose that it gives the real value of the spectral radius. So we start with this eigenvector, an eigenvector of all cyclic permutations of this product, and then step by step we construct vertices of the polytope. It may not converge, and we know simple examples when this technique doesn't work, but by some reasons which not quite well known for us, it never happens in, let's say, in practical applications. So it always works. For usual matrices, it works in a reasonable time up to dimension 20, 25. In non-negative matrices, for positive systems, for positive switching systems, the dimension can be considered up to several thousands. And in this case, it works extremely fast. If you generalize the concept of polytope for positive orthont, so the ordered polytope, it usually has very few vertices, and that's why this algorithm works extremely fast. Of course, I simplify many things there. So the paper is 60 pages. So there are quite technical, theoretical results behind, but the idea is quite simple, I think.
Okay, thank you.
Okay, thank you. More questions? Maybe questions from this room? Yes, Roland, please.
So the polytope can be constructed only if this number of leading combinations is finite, right? So of leading products which give you the...
Yes, yes.
So is this the reason why the problem is hard to compute the joint spectral radius? I mean,
no, it's actually hard even for two matrices. The point is, this is the famous finiteness conjecture of Lagares and Wonk, if such a dominant product always exists. And there are examples when it doesn't exist.
Yeah, I mean, this is the reason why the problem is hard.
Yes, I think so.
Because you encounter, otherwise you could just construct this polytope and then you...
Sure, absolutely, yeah,
okay.
Yeah. But there are some exotic pairs of matrices for which the dominant product, which gives the value of the joint spectral radius, just doesn't exist. It's interesting that there are no concrete examples. So only the existence of such examples are proven.
Thanks.
Let me also just a couple of seconds, because I had to mention it. In the construction of convex, of elliptic polytopes, we used a lot the construction of Nemirovsky-Bental of approximation quadratic problem by projection of linear programming problems. So this helped us a lot to make it efficient. Otherwise, I think we couldn't do it.
Okay. More questions?
I think I have another one about this joint spectral radius. Is there a partial differential equation that is somehow converging to this to a nice polytope, which is giving the norm for which all the operators are contracted?
Last year I would say definitely not, because the invariant Ляпунову function is not unique, so it may converge to another function which is not given by polytope. But now I'm already not sure, because it's possible to prove that in most cases, let's say it's unique. So if this invariant Lyapunov function is unique, this means that it's given by polytope, and probably this polytope can be obtained by as a limit of solution of some PDE. Now I already am not sure that the answer is negative, so probably it can be done, yeah.
Okay, and it has not been done.
But it's unknown, yeah. Until recently, before the uniqueness of this invariant Lyapunov function was, let's say, proved, this question was not considered at all, because of non-uniqueness of the limit. Yeah, now it's known that it's unique, and already possibly this can be obtained this way. Yeah.
Thank you.
Okay, thank you. Let's thank the speaker again. Now we have a coffee break. Since we late at 10 minutes, let's start at 12:10. Okay, Moscow time.